And today we will see in detail the angular momentum operators and their commutation relation. By a definition, angular momentum operator is in classical mechanics, it is defined as the cross product of R and P, that is R cross P. Same thing in quantum mechanics, it is replaced by their respective operators, that is position operator capital R and momentum operator which is I h cross del. Now you can write this in the matrix form ijk xyz px py pz. This is this operator is a position representation. So what is x component? That is ith component. So you have to multiply y pz ypz and minus this one pyz minus minus zpy. So minus zpy. In similar manner, you can write ly is equal to zpx. Y is you multiply this and this, which is equal to zpx minus xpz. Similarly, lz is equal to xpy minus ypx. Now let us take the LX dagger. Whether we will check whether LX is Hermitian or not. Then this you take this expression and take the dagger on left hand side and the right hand side. When you take a dagger operation, this order of the operator will get reversed. So the first term YPZ will become whole dagger will become PZ dagger Y dagger. Similarly, this one PY dagger Z dagger. We can write. So now you can see uh, since position operator and momentum operators are Hermitian operator, Pz dagger is equal to Pz, Y dagger is equal to Y, and also this Y component will commute with Z component of the momentum, so you can interchange. So I am writing this as YPZ. Similarly, here PY tagger will become PY and Z tagger will become Z. So apply the same logic. That is, uh, Yth component will not interfere with this Z. That is Z and momentum along Yth component will commute. So you can interchange. So I am interchanging Z and PY. So this will become minus ZPY. So which is exactly equal to LX. So L dagger X is equal to LX. In general, we can write L I dagger is equal to Li, where I start for XYZ. That means it's a Hermitian operator. That is, these operators are observable. That is the important point I like to highlight. Now we will find the commutation relation between Lx and Ly. By definition, Lx is equal to this. That is, Lx is equal to ypz minus zpy. Similarly, Ly is equal to this one. That is zpx minus xpz. So you can write this. First, you take the first component YPZ. So YPZ with ZPX. YPZ with minus XPZ. So I'm taking minus out. It's a multiplicative factor. I'm taking minus outside of the commutator. Uh, then minus ZPY. I will take this term. So minus I'm taking outside the commutator. ZPY, ZPX, this one. And ZPY is the second term. ZPY, second term. Minus of minus will become plus. So ZPY XPZ. Now is well established one. The Xi Xj is equal to 0. That is any component of position will commute with each other. Similarly, this Pij is equal to 0. That is x component of momentum will commute with xyz component. Or y component will commute with all other component. So this is always equal to 0. Then the position and momentum, commutation of position and momentum, both are in same direction, then it will not commute. If it is different direction, it will commit. It will obey the canonical rule. So, commutation of xi with pj is equal to I h cross delta ij. When I equal to j, this will be I h cross 1. Otherwise, this will be 0. Now you apply these three fundamental rule here. You verify the first term. See, here you have pz component and here you have z. So this will not commute. So you take this as it is. What about this? You have pz, position, momentum along z direction. There is no z component. So this will commute each other. So this will be 0. What will happen this here? uh, there is py px. There is no x component or y component. Since there is no x or y component, this will be 0 because all will commute. That is x component of momentum will commute with y component of momentum, and naturally x component of momentum will commute with yz component. So like that, it will not commute only in x component. This will not commute with y component. There is no x or y, so this will be 0. Then what about fourth term? You have pz here, you have z here, so this will not commute. You take first one as well as the last one. So first one, because they will not commute. So I have taken first one and last one. Now use the commutation rule. This is px is a commutation operator. First you take this one. So px is a commutation. Px is a right hand side operator. So I am taking right hand side as per commutation rule. And z is left hand side. So I am taking left hand side. Same thing is with this. You take this one pz right hand side, x left hand side, x left hand side. Here you can see uh, there is a what are the component we will get 0. See here you have p x p z. There is no x or z, only y is there. So naturally this will commute. So naturally this will be 0. Then what about this third term? You have y component of momentum. So there is no y here, only z and x. So this will become 0 because it will commute each other. Then only fourth component, you have pz and z. So now you expand this. First you take y outside, then you will get pz. So which will not commit. If we take pz in this other side, yz will commit. So no problem, you can take only y. There is no meaning in taking pz out. Naturally, y commit with z. What will happen here? If you take z outside the commutation, so naturally py pz that will become commute, so that will be 0. Only if you take py outside, that is py is right hand side operator, you take py right hand side, then z with pz will not commute. So now we got the result y commutation of pz with z px plus x commutation of z with pz, then this multiplied by py. Finally, we got this expression. What is the commutation between pz z? It is minus IH cross. So, you know very well this is minus IH cross. So, you are taking minus IH cross first because it's a constant. Then Y PX. What about this? Z PZ is plus IH cross. This is plus IH cross. Then naturally this will become IH cross XPY. So now you take IH cross outside and take the positive term first. That is XPY minus YPX. So what is XPY minus YPX? It is nothing but LZ. So LX LY is equal to IH cross LZ. In similar way, you can prove LY LZ is equal to IH cross LX. Similarly, LZ LX is equal to IH cross LY. If order is changed, it is not cyclic. Here it is cyclic XY, YZ, ZX. If it is not cyclic, say for example ZY, YX or XZ, then instead of plus IH cross, you will get minus IH cross. So this can be written generally that LI is equal to commutation of LI with LJ is equal to IH cross epsilon IJK LK. Here this epsilon, uh, you know the meaning of epsilon. Any two are common. If ij is same, then this will be zero. Ij is same. If ijk is cyclic, then this will be plus. The symbol will be plus. If it is not a cyclic, then it will be minus. So you remember that the orbital angular momentum comes under Lie group. Similarly, the total angular momentum comes under Lie group, and the spin angular momentum also comes under Lie group. Whatever rules applicable to the L is equally applicable to J, equally applicable to S, because all comes uh, under Lie group. So that you have to keep it in your mind in order to solve so many problems in future. Now we will see the commutation relation between L squared with Lx as well as Ly Lz. First we will see the commutation between L squared with Lx. L squared can be written as by definition L squared is equal to Lx squared plus Ly squared plus Lz squared. Here naturally Lx squared will commute with Lx. So you can remove the first term. This term you can remove. Then naturally L squared with Lx, commutation of L squared with Lx will become Ly squared plus Lz squared with Lx. So this can be written as into this can be separated into two commutation relation: Ly squared with Lx, Lz squared with Lx. You can take this as Ly into Ly. So you take the right hand side operator right hand side and left hand side operator to the left hand side. So the first one can be written as this. First as shown in the first rectangular yellow color box. Same thing is here. Lz into Lz. So Lz you take left side first, then Lz you take right side. Now you will have four component. This Ly you keep as it is. What is a commutation of Ly with Lz? Yx, remember sir, that this is not a cyclic. So this is minus IH cross Lz. That is what I have written. Then what about this Ly? Already there is Ly here. So minus IH cross Ly Lz. Then what about this one? Ly, commutation between Ly Lx is equal to minus IH cross Lz. Minus IH cross Lz. Already there is Ly. I have written. Minus IH cross Lz and this Ly you will get. What about here? Here Lzx, it's a cyclic one. So naturally this will be IH cross Ly. So this can be written as plus IH cross Lz is comes first, then Ly. Then what about this? Lz Lx is equal to IH is a cyclic. So IH cross Ly. So this will become plus IH cross Ly, this Lz. Now this first and fourth term will get cancelled. First and fourth. Because both are equal and opposite in direction. Same thing, second and third will cancel with each other. These answers. So L squared, computation of L squared will with Lx is equal to 0. That means you can measure L squared, eigenvalue of L squared and Lx simultaneously. So whatever valid for Lx is equally valid for Ly, equally valid for Lz. So we can generally write this as L squared computation of L squared with Li, where I is equal to xyz is equal to 0. I have already mentioned that this will be true for all Lie group operators. That is, it is equally valid for J and S. Here I like to highlight, though the Lx and Ly are observable, we will take Lz as a reference. So always in quantum mechanics, we will take z-axis as a reference axis. So commonly we will take Lz as a reference axis. With this introduction, we will move on further. Thank you very much for watching my video and supporting me continuously. Thank you very much.